All right, ladies and gentlemen, thanks a lot for hanging in there. I think this is just going to be the fifth chunk. I said there'd be six, but there's a half hour left. I think we'll just power through to the end here. There's a little question regarding the change in temperature versus the absolute temperature. So this is degrees Fahrenheit, this is degrees Celsius, this is Kelvin, and this is Rankine. In every case, we were just dealing with little tiny delta T's up here, you know, and we know that 1 degree Celsius equals, what is it, 9/5 or 5/9? 5/9 of 1 degree Fahrenheit. And it's the same thing, 1 Kelvin equals 5/9 of a degree Rankine. I got my degree symbol on the wrong side there, but that's really all there is to it. You're just looking at differences. Okay, now, I told you I would talk about enthalpy. I already mentioned the word entropy. Entropy is not something you're going to need, want, or measure unless you're a poor academic like me and, you know, have nothing else better to think about. But enthalpy is, I like to think of enthalpy as just heat density. We already did a problem before where we looked at the material density, just kilograms per cubic meter. Enthalpy is just heat density. And it's just measured in joules per kilogram. So let's take one, you know, pretty simple example. I've designed and built these before. Let me just show you one thing that maybe you'll encounter in your own sustainable building design careers here. I've designed these before. I've seen them built. The one that I designed was not funded, so it did not get built. But my moonlighting job is as a professional engineer, so I've done a little bit of consulting. And what these guys were working on was a trom wall. And let me just show you what I did for this, because this is a great example of enthalpy. So what I did, I started with the amount of kilowatt hours per square meter of sunlight that's going to hit a building. And that just happens to be the solar resource that we have available to us in Missoula. You can then say this is how many kilowatt hours per day you're going to get for a given area, et cetera, et cetera. Here's the rate of electricity. Here's that $10 per, and this is the weird unit. It's MCF for 1,000 cubic feet. I used a K before, but yeah, and you can drive yourself crazy with all these heat units. But the conventional unit is MCF for 1,000 cubic feet, and that's maybe French for mille. You know, that's 1,000 in French. So anyway, but what I did, came down here. I know they are. Always messing with this. This is just, it's smoke and mirrors. I also came down with the number, I mentioned before, the number of heating degree days in this particular building for how big it was and how hot they wanted to have it. There's my heat capacity of air. We saw that earlier. That's the density of air. This is the volume inside the building. That's the change in temperature. Here is the heat transfer that we just saw, et cetera, et cetera, et cetera, et cetera, et cetera, et cetera. I did a solar pathfinder analysis to see how much radiant heat was going to come in. I ran a little spreadsheet to see what the actual numbers would be. Here's an example of a trom wall. And what you've got is something that's facing south. So you could, there's a lot of great sunlight coming in these south windows right now. And, you can think of, rather than at night letting all this nice heat that comes into the building escape, you actually store it in some massive body inside the enclosure. In this case, these clients wanted to put a bench there, so you sit down in the winter and your tushy's all nice and warm. And what we've drawn here is a way for hot air that's trapped between this glass and this reflective surface. It is then forced up through the bench, forced up, and you don't see it too well here, but it actually returns. There's a way for this air to come through, go up, and then just sort of return and circulate. So this air that's coming up is in contact again through conduction with the colder air inside, and it's just its own little weather system in there. You know, it's hot on the left, it's forced through, comes up through, gets cold on the right, and comes back down. So that's your trauma wall. Now, at night, if you make this out of something relatively massive, stone, what have you, that heat will then stay inside the building. That's the idea. That's the idea.
So it's like a rocket stove mass air heater, but just using the sun.
Yeah, you got some mass in there. Yeah.
They designed that when they built the pipeline in Alaska.
Oh, really? Okay.
So that they keep the thermofrost so it wouldn't thaw.
Yeah.
The oil was 110 degrees.
Yeah.
And it would lose like 8 degrees over a 200-mile area. So they designed
little heating stations?
exactly what you're saying.
Okay, yeah.
And it would take the heat from the ground and dissipate it into the air. And it was a closed system.
Keep that pipe, yeah, neat, cool. I threw a little, so here's basically your wall, your thermal mass, and then this is, what I was trying to do is put a little awning design in, because in the summer, you don't want that thing cooking, so you can adjust it and lower it. So that's the trauma wall. Did a little energy economic analysis. I built a little mock-up with some junk I had laying around the house. And here's another example of the trauma wall with your air gap, your nice thermal mass. So let's actually just calculate, for example, what the enthalpy would be inside a relatively large concrete trauma wall. So let's let this thing.
Your M stands for British thermal units.
What's that?
Your M, CFM, or MCF, is a million thermal units British.
No, in that case, it's actually 1,000 cubic feet.
Yeah, I know, but the M correlates to a million cubic thermal units, and the M is the ancient letter for.
Oh, okay, there you go. Yeah.
4,000.
Right, from Romans. Gotcha. Nice, gotcha, cool. Okay, so let's just say we've got a concrete wall, and we're gonna go back to our heat equation, and so we're gonna need C sub P for concrete. We're gonna want to know the total mass of the concrete. And if we know the change in temperature for the concrete, we will then know how much heat is in there, and we'll essentially know the enthalpy of the concrete, right? So let's just go out and find that stuff right now. Heat capacity of concrete. I think this looks like it's the back to the engineering toolbox. So we already looked at air before. Let's just bop on down here to concrete. Stone. So we're looking at, I'm just going to call that 0.2. Now, it's maybe a little surprising, but let's just compare that to water. Go down here to water. I believe water's higher. Let me see here.
Never H2O.
Oh, was it? Diamond, cement power, clay, 0.2. Let me pull up another one. So heat capacity of concrete is 0.2. Let's see this for water. Yeah, it's 4. It's much larger. So it would almost be better to build your trom wall, if you could, out of water. A lot of times you'll see people do that in their greenhouses. Yeah, so,
The thing about that, though, is if it gets too cold, you're going to blow everything out.
it's true, but what you're going to do is have this whole thing inside your house. So as long as you're not going below freezing, you should be in good shape.
Funny, I was thinking that same thing about a project I'm working on this morning.
Yeah. So, just looking at all these different substances, I don't see anything with really heat capacity anywhere near what water is. All these guys are down in the 0.2s, 0.3s, et cetera. So,
Propylene glycol.
Propylene glycol, isn't that stuff they spray on airplane?
Yeah, it is.
yeah. Propylene, and you also see a lot of propylene glycol in solar thermal systems in Montana because it won't freeze. Okay, but let's just go back to our concrete. Again, it's 0.2, 0.2. The mass of the concrete, I'm just gonna throw a number out there and say it weighs 10 tons. You can imagine a 10-ton wall. So that's 10 tons, and I'm going to use SI units again. This is going to be 10,000 kilograms. 10,000 kilograms, that's 10 metric tons. And then the change in the temperature, let's see, maybe we can get that, wall up, shoot, I don't know, maybe 40 degrees greater than ambient. So we'll call that 40 degrees F, because you've been pumping heat into it all day. Give me that in Kelvin there, would you, David? Oh, it's like 22, right? Because I think 40 was 11.
You want it in Kelvin?
Or Celsius, either way. Actually, I mean, I need it, it's a delta T, so I guess I'm just multiplying this by 5/9. So 40 times 5/9, I think is going to be 22 Kelvin. And I want to go back and double check that, I want to get the units. So I said 0.2. Again, we're trying to figure out, There we go. Oh, I see. Okay, you know what? I see what went wrong before. That's what I was looking at. We actually want to be in this column. I was a little surprised, like, why is nothing anywhere near water? Well, it is, because I was looking in the BTU per pounds mass column. My apologies. So let's actually go down here and look at, I'm glad I checked, because you got to do the units. That's the third part of every problem. So let's just go back down and look at concrete and change that 0.2 to, I'll just call it 0.8. So again, nowhere near water, but it's closer. I'm just going to call that 0.8. Some things, actually, you just kind of remember, but this is not one of them. .8. Let's double check our units.
It's hard to remember, you gotta try to go through the interval to get to that point.
Kilojoules per kilogram Kelvin. There we go. Kilojoules per kilogram Kelvin. A lot of K's flying around there. But we have our mass of our concrete in kilograms. We've got our delta T in Kelvin, and we should be good to go. So in this case, the heat content equals 0.8 kilojoules per kilogram Kelvin. The mass is, 10,000. kilograms. The change in temperature is 22 kelvins. So let's run that on the calculator. And that's just going to give us how many kilojoules of energy are in that 10-ton block of concrete. So 0.8 times 0.22. Is that what you got? Or no, did I do something wrong?
I got 176,000.
Let me run it again. I might have left a zero out. 0.8 times 10,000 times 22 equals, okay, there we go. 176,000 joules. Kilojoules, thank you, yeah. 176,000 kilojoules equals 176,000 kilojoules equals 176 megajoules. Perfect. Now, let's just bop out and figure out what the enthalpy is. It's also worth noting right now that enthalpy is it's an extensive property. You can have more or less of it, just like you can have more or less mass. Heat is an intensive property. You can just kind of keep pumping heat into that wall. So if you get a chance, go out and look at the difference between extensive and intensive properties. But for now, let's just look up the definition of enthalpy. I've been promising this all day long, and here we are finally. The internal energy. Okay. Let's just bop down here.
You know, the room with how we built the Parthenon or something like that, they used that and then made it less and less so they could form the dome.
Say again?
The Romans,
Yeah.
that's how they constructed the dome.
They came up with the dome for minimal heat loss, is that what you're saying, or? Yeah, sure, yeah. And if we went back and did our house example, and we took our house and changed it from a box into a sphere, same square footage.
The round hole there is the same aspect of.
Heat, just a little heat transfer through the top? Yeah, yeah, yeah. Okay, so there's a couple of different ways to look at enthalpy. One is the, just as a extensive variable, like I just mentioned. Another way, and that's why I've been writing it as little h. So this is the total heat in the thing. But if we now, and so right now, all we're looking at is the internal energy, and this can be a number of things. For now, we're just worried about the heat. If this were a gas, and you were squishing it, as you squish a gas, you're putting energy into it as well. So, and another way of thinking of that is heat as well. But for now, what I'm going to do is just write it as a lowercase h. So the big H, as we see here, is the total extensive enthalpy. The little h is the intensive. So I'm just going to write that as, I'm going to keep it as, let's keep it as kilojoules per kilogram. So 176,000 kilojoules. And now you've got 10,000. Oops, I wrote that as grams instead of joules. I was thinking ahead there too much. So, 176,000 kilojoules divided by 10,000 kilograms. Just start knocking zeros off of there. 176 divided by 10. Let's change that right there. Equals 17.6 kilojoules per kilogram. So now you could say, well, if I were going to, maybe you come up with something fancy, and if you've ever seen those salt blocks, they do a pretty good job holding on to heat. So you put them in your fireplace at night, and then you stick them in your bed, and you keep your feet warm or whatever, so you don't have to wear socks. You can imagine a trom wall. We're like, hey, I got little bricks on my trom wall, I'm going to take it off, and you can have a couple, you can say, well, how much energy how many kilograms do you have? Well, if I got 10 kilograms, then I got 176 kilojoules of energy. So that's enthalpy. In fact, it's more or less specific enthalpy. It's heat per unit mass. Okay. Now, we got about 10 minutes left. I already talked a little bit, and I'm going to let you explore this on your own. There's another, and this is kind of weird, and I hate to do it to you this late in the day, but there's another thing, H, called the heat transfer coefficient. Now, what's that? Well, that's just how, it's a term for convection. So your body does this all the time in the summer when you're working out or you're hiking or whatever, you get sweat. The heat transfer coefficient will tell how quickly convective heat will move away from you. I'm not gonna cover it right now because I want to get to the R value, but I know it's discussed in your book, so let's just take a quick look at it and explore the units quickly. So we already know, and in some ways this looks a little bit like, and I apologize, I'm sorry, it's the same letter H that we just used for enthalpy, but and it's just, yeah, somebody just ran out of letters, but there it is, but it is standard.
There's only 23 of them.
There, I know, there's not enough.
Gotta start reusing.
Yeah, I know.
Recycling.
Yeah. Put funny squiggles on over there, yeah. So this Q is the same one we saw before, and that is how, it's how quickly heat is leaving. Remember we did that concrete house example, there was the 18 kilowatts was leaving. The heat transfer coefficient is the amount of heat per temperature. So you could have some substances where you have a very high temperature difference, but a low heat transfer, which in general is kind of what you want. The opposite example is sweating, where you might have a very low temperature. I mean, your body's 98.6, it hits 110, and you're feeling it. I mean, that's a very low, it's only a 10-degree temperature difference, but all of a sudden you're like, hey, let's make some sweat to get rid of this heat, to pump out some more Q. So the heat transfer coefficient is just the ratio between how quickly heat is leaving and whatever the temperature difference. So that's a convective term. Okay. Now finally, let's get into the R value, and then I'll let you go. And I'm going to do it in this way, because I know your book talks about these guys. I don't think this is going to be that good, but let's just see what happens. Yeah. Let's do it this way. R value versus K value. Text and specs. Actually, let's do it this way. I know I've got a pretty good set of notes on it. All I want to do is show you, oh, yeah, here's something to think about. I know a few of you have taken DC circuits before. Okay. You can think of R values a lot like resistors. It's pretty easy to think because it's the same R for resistors. If you have R20 insulation and you add another R20, you get R40. They just add just like resistors in series. You would never add thermal conductivity in series. That's why they just said garbage. It's one over the other. So that is something to keep in mind. And yeah, here's the next one. This is what I wanted to show you. We went to yeah, so right there, perfect. That value of U is a lot like the value of K that we did before. What's the difference though? What's missing there? What do we have to use with K that we no longer have to use with U? Do you remember? No. Well, watts and joules are bound up in that U the same way that they were bound up in K. The only thing that's missing there is that thickness. Remember the S, when we were running around with K a while ago, the only difference between using the U value, and I guess he just calls it the conduction heat transfer coefficient, instead of K, which was the thermal conduction coefficient. So, and I'm not sure there's a standard, but the point is, for K, we were able to go online and look up the different K values for different materials. It's not always the same for U. And the other thing to keep in mind is U is just 1 over R. So in your day-to-day life, you're always going to be wanting large values of R, which just means you need small values of U, or small values of K. And remember we did that one for iron? We're like, oh my gosh, the K value is too high. It's going to leak R. That just means the R value is too low. So that's really all I wanted to show you between K, R, and yeah. Well, I hope that helped. I know there's a lot of variables flying around there, but when push comes to shove, if you know all this stuff and the next guy doesn't, you're going to be more valuable. So thanks a lot.
What? The way that I've always figured it out.
Yeah.
I've always associated that volts and amps.
Yeah.
Yep. Exactly the same thing.
It is.
Take the volt, or you can decrease it, the step down.
Yeah, it's a thermal circuit. Yeah, it's a thermal circuit versus an electric
Exactly the
circuit.
same thing.
Yep.
Have you ever thought about taking that little schematic that you drew
And it
for
makes
the
it
house
simple.
and like take
If you-
and
if
go
you
out
own
to like a
it,
city and make it for this is the energy line for the city
And you
and
can
then this
convert
is,
that to anything. You can convert that to
this is the
gallons.
power
Yeah.
for all the city and then this is
Convert
the
that
energy
to
that all the city uses. You know, like a girl with the curling iron.
Get a little artsy with it.
Yeah.
Yeah. No,
I'm like seeing the big
Oh,
city.
trying to do all this shit in my head.
that's all right.
Also,
Whatever works.
have you
Well, I mean, but
been
then-
and looked at
you got
the greenhouse that we
things you
built
would do it.
behind the
Yeah.
sea?
Oh, I see what you mean, you're
There's
forced to.
behind
Yeah.
Low Mason.
Low Mason. Yeah.
The stucco wall in there, what we did is we took road mix, basically asphalt, and we put it in bags. And then we set the asphalt in on top of each other.
Yeah.
And we stuccoed the wall back, placed with the mud stucco.
Nice.
But I'm thinking that your wall, I'm blanking on the name of it.
Trim wall.